The title of the presentation is Interactive Zoom Panning from Live Panoramic Video, and as he mentioned, we come from a nice lab in Oslo. It's me, Ragnar, master student sitting over there, Sigurd is another master student, and Carsten and Paul, I think, is quite familiar with this community. And then we collaborated with University of Toulouse with the Computer Vision Laboratory with Pierre. He's an established publisher in computer vision community, and Vincent is again from the multimedia systems community. And that's me, the one in the golden. You can just call me Vamsi if you want to ask something. So when it comes to real world, what we see is that it contains of some field. Let's say that you can capture something really as narrow as that, or a bit wider, you can capture a space in a room, or a bit more wider, something like a football field, or a 360-degree field of view. The problem is that real world really doesn't have a limited field of view, but most of our display devices do. So how do we work around this solution in current days technology? We either have a disconnected observer, a user who doesn't control what kind of part of this wide field of view he is watching at, or really distorted images that they still use. I see some disgusted faces around. And either too much information in a small field of view, packed so that you don't really make anything out of it, or use of multiple display devices to try it together. And the last one, you need quite a lot of money for that. So what we wanted to try is to provide the ability to be able to be your own cameraman virtually. So what we wanted to try is that if the audience here one of them wants to decide that they want to see that part, and the other one decide the other parts, so they should be able to freely do this on the field and from a remote location. So coming to that, I want to show you something, if that is possible or not. Where is this? There you go. So this is a demo. This is a virtual client, and you can install this on your machine too, provided you have some Linux-based operating system. If you haven't heard of Windows exactly, you know what it is, but yeah. The demo is that way. Well, and that's about the presentation. But since we have time, I'm going to share a small story with you guys. So this is a story time. As every story, we say a long, long time ago, and in a far, far place. Okay, let's take it 1 year and 18 days, and 13,225 kilometers from here. I think that marks down to the MMSys 2013 that happened in Oslo. What happened was that there was a guy that looked quite similar to me, making a presentation of our previous system. So I made a lot of promises there, like I always do in our presentations. To put you in context, I'll give an overview of the architecture that we have. So we have the Toulouse Stadium up in Tromsø, really, really north, kind of close to Oslo. And we have a few antennas that collect data from each of the players. They collect position data, their velocity, their heart rate, and some more player-related information, and it's stored into a sensor subsystem. And then we have a few cameras that capture whatever is happening on the entire field all the time. So the idea is that we will be capturing the entire field at all times. And then it's stitched into a panorama, and we store it in the video system. And then we have an expert, a coach. Usually he gives out his own annotations. And then we try to give some sort of interactive power to user based on this. Well, this is what I presented last year. So in that part, while we were presenting, we also worked on the real-time panorama creation. We take 4 wide-angle cameras, you can see, and then we just undistort them, warp them, find the dynamics, and stitch them, and then voila, that's the panorama. So what happened was when I presented that, I got a few questions from the audience. And just because I don't want to show their identity, I kind of photoshopped their faces. So the first one, he asked us, where do you think we are heading with all this kind of setup? And the second one is, how do you plan to use all this setup? And the third one, or this was the last one, said, where can I find differences with existing panoramic capture system, and how is your system exactly different? I don't know if one of these is in the audience, you probably recognize yourself. And so what we tried is to experiment with different representations of panorama. First we tried the perspective panorama, and then we thought what next, because the questions were kind of serious. So we said, okay, let's reproject it onto a smaller display. For perspective panorama, what we had to do is simply crop the panorama. So you have this panorama, and then you crop it. And the problem is that there are too few pixels on that side, or you send a lot more pixels on this side, which are redundant. Whereas you actually don't capture it this way. It's just that they're interpolated and then they're represented that way. So we thought, can we actually do any better than this? And so we thought the natural way is either using a spherical or a cylindrical projection. Cylindrical works because it's a wide field of view. If it were similar field of views on both the x and y axis, then spherical would work better. So what we tried is that we just tried to make a model of a virtual camera, try to project a ray through it, and then see where it lands onto the cylindrical texture, and then fetch those pixels. So we tried the initial execution, even though it looks simple on that figure, it wasn't that easy, let's say, converting it into code. So we used MATLAB first to get it to a bit lower level than that figure. And then we used OpenCV, C++, and a single-threaded simple CPU execution to try to achieve. Then we set out for execution. What we got is this. So when that happened, the obvious reactions were, well, mine was happiness. And Carsten, he's an expert in multimedia systems. And he goes, wow, that's amazing. And Paul, he knows, he has seen, probably I can assume that he has seen most football than all of us in this room. And Pierre, he's an actually expert in computer vision. He published in CVPR, ICCV, CCV, all good computer vision journals. He says nice. Well, the master student wasn't impressed with this. So, if you think about it, there has to be something wrong with these guys to say that it's actually nice, or there has to be some underlying thing in this video that helped us to the next level. That was the core part of what we were trying to guess. And when we actually solved this, we were sure that we can get quite further. And then we got into the details, because the devil is in fact in the details. So what we did is we replaced the 4 1K wide-angle cameras with 5 2K cameras that were a bit narrower. And we used multiple capture machines. The idea of using multiple capture machines is that you can extend from 5 to 50 cameras or whatever you want to use. It's the same system, it's just throwing out a bit more money on it. And we did a better H.264 compression because of the part that I'm going to explain later. And we have an HTTP video segment server that feeds to the client that's remotely located. And we also made an auto-exposure synchronization, which means that all these cameras on the fly get an auto-exposure and or exposure synchronized. So the camera array looks like that. It's the advantage of 3D printing. And the real technology, what we do is we fetch video segments from the HTTP server. We decode those video segments, we create virtual views, and we bind the output to the texture buffer. And we also handle the input, like if it's a joystick or a game controller or a keyboard, or yeah, it can be anything. Now, in the viewer, when I say real-time online mode, it's a bit delayed. Let's say that it's 2 or 3 seconds delayed from the live action. But if you think about it, it's not that bad. And it's a multi-threaded pipeline architecture, which means that it's fetching the segments in the background, it's handling the user input in the background, it's decoding on the foreground. But there is one major thread that's decoding and displaying. And then we optimized it for better performance using the texture memories on GPU. And the irony is that our weak link is a network. So we don't have any control over the network, and we don't know what traffic shaping can happen over the network. So summing out whatever I said so far into an image, it looks something like this. So you have several cameras, several capture machines, and then there is a processing machine that stitches the panorama, and then it puts out the link for the net from anywhere to access. And then you can use, well, we show a tag there, but we don't really have the application on the tag, but we have it on laptops, PCs, and yeah, you can install it on any machine that has a good enough capability. And once we are done with these improvements, the panorama video looks something like this. Well, I had to scale it down quite a bit so that the computer doesn't complain. And the same reprojection video looks something like this. You can actually see that it kind of replicates a physical camera's movement. It doesn't look that bad. Now, what's the big deal with all this? Well, that is a big deal. So the actual system, we have it in Tromsø, and we try to run the client in Oslo. So it says that it takes about 22 hours and 19 minutes of drive, 1,600 kilometers, or if you fly 2 hours. That's a long distance. So we actually tried, and unknown network, that's where the unknown network comes from. We actually tried the entire system over this, and we did succeed to run it in real time. So these are some of the performance graphs. You can find them in the paper as well. We tried with 3 different networks. One is the wide area network, which is from Tromsø to Oslo itself. And of course, we tried with local host where the server runs on the machine itself and local network. You can simply see that the file download time is, well, it is kind of random, but it also follows a bit of pattern from the file size itself. And since the rays can never land on a specific integer pixel, we had to do some sort of interpolation. And we tried with different ones, the nearest neighbor, bilinear. Well, the CUDA textures provide you with optimized bilinear fetching. So you can actually see that the bilinear is a bit faster than the nearest neighbor. And then bicubic, it's not that far, so we just pick the bicubic whenever we are running the system now. And we tried some experiments of changing the virtual camera size and showing what execution times we get. So you can actually see that if you have a smaller device, you can use lower capability hardware for actually doing this. Now, just like the way we were working on things while presenting for the MMSys last year, we did work on things too. So what we are working on now is adaptive streaming so that we don't stress the bandwidth so much. Like for example, if you have a lower bandwidth, we want to be able to provide a lower quality panorama so that the file sizes are lower. And well, this is exactly why what we are going to do, and the effect of which was my PC, because we use the CPU now to encode and decode the panorama videos, and they are big. So as an effect, it got overheated and it burned itself out. And when it's sunny and when you have open stadium, you have strong shadows and strong highlights. So we are currently developing the HDR. We are able to capture the videos at 50 frames per second. We are alternating every frame with one of a lighter exposure and one of a darker exposure, and we capture a video of 25 frames per second, which is kind of a high dynamic range. And then of course, we're dealing with the system aspects of it, the robustness and replicability. Replicability is quite evident. We actually took a smaller version of the system here. If you guys want to try it out, you can come to the demo session. It would have been nicer for me to show it out here. It would have made a nicer impact, but yeah, unfortunately, it didn't work out so well. So I'm going to show you two videos. If you pay close attention, they're going to be of the same sequence, but I want you to pay attention to the movement of the virtual camera. That's one video. That's the second one. So, which one would you prefer? Second? Well, then we are already on to something, because the first one is recorded by an expert who had years of experience in recording football, and the second one is a machine-generated one from the code that we wrote. So we worked on this after the paper submission and everything, so we didn't put this, we just put a small link if you guys read the paper. So yeah, we are working on developing automated technologies. It's basically about taking the abstractness to a higher level. So when I say interactive zooming and panning, you have to, for this system, the one that you can try now on this laptop, is that you have to move the virtual camera manually yourself. So if I want to take it to a bit of higher level of abstraction, saying that follow the ball for me, or follow these players for me, or follow that specific team for me, then we are developing the intermediate algorithms, the intelligent ones, that can create a smooth path for whatever query that you have selected. And like every other story, so we present a real-time system for interactively zooming and panning into panoramic videos. And we tested the client on multiple platforms, Mac OS X, Linux. It's easy to replicate. It takes hardly 1 hour to 1.5 hours to set up the whole part, not the client part. The client part is downloading the code and compiling it yourself. The server part, it takes about 40 minutes to set up. And of course, it's cheap. That's the main difference from the other existing systems that show this kind of quality around. So that's the end of the presentation. Yeah.
So, what are the bandwidth requirements at the moment? You need a...
Oh wait, for now, they're really high. The video sizes are approximately 9 megabytes for 3-second segments. So you can calculate that. They are quite high, but there are 5 cameras, so it's close to 5,000 by 2,000 pixels for the panorama. And we are using only one iframe for the segments.
There's a lot of soccer fans in Africa.
Have you tried with spherical cameras? It seems that CES they were releasing spherical cameras.
Yeah. We didn't want to limit to a specific number of cameras for exactly one reason. Because if somebody says that they want a higher quality when they zoom in, then we have to go for a higher number of cameras. With this kind of system where we use actually multiple machines to capture, and we have 3 machines, one of them is connected to 2 cameras, one of them is connected to 1, and the other one connected to 2. So you can just plug in more cameras in there and you get a higher resolution panorama.
Yeah, I was talking about spherical cameras that
Yeah.
put it in the middle and then they just
turn the things around. We haven't tried it because the problem is that, to be honest, we haven't tried it because of the engineering part, let's say, because we have built all of this ourselves.
Yeah.
And we didn't get to try the spherical. Yes?
Oh, yeah. Besides, using for football watching, are there other applications or potential application areas you're exploring?
Yes, we are exploring them, but we haven't tried them yet. There are 2 direct applications that we are exploring. One is in the medical videos, like when you swallow this kind of wide-angle camera pills or wide-angle cameras that they send into your stomach or into your other part. you have this really ugly looking video that you don't have so much of control about, and it's doctors that can look at it, but it's really distorted. So you can really apply the system quite clearly to such a application, and you can have a doctor somewhere else on the planet and he can actually look through clearly. Putting a doctor inside you doesn't sound politically that correct, but it's the kind of thing that we are trying. And the second one is that I spoke to people at Cisco. There was a R&D guy, he told me that they can find a direct application to the teleconferencing. If you have a wide room, for now what they do is they either use multiple screens to show all the people, or they just switch the cameras to whoever are talking. So instead having such a aesthetic or smooth kind of movement is already good enough.
Thanks.
Oh no, I mean, you could probably use it for security applications as well.
Exactly, but I don't like surveillance so much.
Yeah. Have you heard of the Oculus Rift, which is a virtual reality helmet?
Yes.
So this seems for me like a perfect application. So when you choose your field of view by moving your head, simply, it just has to be really with very low latency. So what is the lowest latency you can maybe get? Because I think it should be below 30 milliseconds or 60 milliseconds.
Which
Well, for the
latency
helmet,
are you
like
talking about?
from the movement to what you see, this
Or
has to be very low latency.
That hardly takes 10 milliseconds.
Okay.
So it's nothing. When you say latency, I assume that from the real
Oh, no.
happening to
From the movement to what you see.
yeah,
And that
that's
seems to be the
hardly,
perfect application.
yes, that hardly takes any time.
So do you stream one stream to all users, or multiple streams to each user, or multiple streams to each
Yeah,
user?
we tried doing that. The idea of creating the virtual view on the server and sending it, but it immediately puts a limit on the number of users that you can get. On the other hand, if you put proxies, you can just stream your panorama to as many users as you want.
But it's one panoramic for all of them?
Yes, it's a single representation. It's simple.
So what's interactive or what's it?
The virtual camera.
So all of them are using the same view?
No, they have their own virtual view. So, for example, if I send the panorama to you, if I send the panorama to Paul, if I send the panorama to Pierre, you can create your own virtual views. The intermediate representation that you have is a panorama. It's the entire information. From there, whatever you segment out is happening on your side.
So for creation of the panorama, how many views are embedded in the creation itself?
For now, it's 5 cameras.
And you send all 5 cameras in section?
No, we send the stitched panorama. So it's we don't switch between the cameras. From what you asked, I think that's the question. We don't switch between the cameras. We make an intermediate representation so that you can smoothly move the camera around. If we just switch the cameras, it's just a matter of sending all 5 streams to somebody and just selecting the stream, whatever they want. But that won't replicate the actual physical movement of the camera that you have seen here.
So you have 5 physical cameras?
Yes.
And you create 5 other representations from these cameras and you stitch them together and create a panoramic sort of component or stream and send it to the user who can generate multiple views from them, or even more than 5.
Yeah.
That's correct?
Yeah.
And the last question before we have the meta questions.
So when doing the scene is quite complicated, not just soccer game, but how about in some festival and then some kind of parade, there are lots of people moving all simultaneously.
Mm-hmm. Do
you think your system will handle the kind of complicated thing?
It should. I don't really see the problem.
Okay, because well, the quality of images and the processing time will be all different, right?
Well, it depends on the size of virtual view that you're creating. So if you want something for your cell phone, for instance, where you can see maybe a 640 by 480 resolution or even a bit bigger, it hardly takes any time. But if you want to create a full HD video on the other side, like 1920 by 1080 pixels, then it's a lot of ray intersections that it needs to find. So that takes a bit of time or higher than the processors.
Okay, thank you very much.